All right, so section 9.3, independent samples for two means. So this section will look at how to analyze means when two samples of quantitative data are collected that are independent. So as with all other hypothesis tests and confidence intervals, again, the process is going to be the same. The formulas and assumptions are different. Okay, so we're still going to be using phantoms for hypothesis testing, panic for confidence intervals, and all the formulas and assumptions are on your cheat sheet. Alright, so these next two pages, again, are just your reference pages for the hypothesis test and the confidence interval steps and what they look like specifically for this particular test. So again, hypothesis test, we're following through phantoms. We're dealing with quantitative data. So again, we've got mu's and x bars, so our parameters, there's mu1 and mu2. And we're going to get information about those from our random variables x bar 1 and x bar 2. Two-tailed, left-tailed, and right-tailed tests for our hypotheses. Again, now we've got mu1 and mu2s. We do not talk about mu sub d when we don't have dependent samples. Our assumptions here are pretty much the same as what we had before, only now we're, so when we did just the t-test for one sample in the couple chapters ago, only now we've got, again, kind of double duty. We've got two groups of data to analyze. So again, now we're going to assume that we have a simple random sample of size n1 and n2. In this case, the samples have to be independent to run the two-sample t-test. If they're dependent samples or paired in any way, then we run a t-test on that list of differences. But in this case, if there are two independent samples, we're going to run the two-sample t-test. The next condition is we either need a normal population or a sample size of at least 30 with no outliers for each group. So again, it's a double whammy. We've got to check it on both groups of data. So we either need population 1 is normally distributed, so either it's stated or we've got data to run those checks on to assess normality, or little n1 is at least 30 and we don't have any outliers. And then for the second group, the same thing. We either need population 2 needs to be normally distributed, or little n2 has to be greater than at least 30, and again, no outliers in that data set either. And again, just reminding us about the techniques from Chapter 6 to assess normality. And then in this case, we need the population standard deviation needs to be unknown for each group, which again, that's almost always the case. So again, if those conditions are met, then we can run the two-sample t-test. Okay. All right, so now our T in phantoms is test statistic, and before we look at the standardized test statistic, just the statistic from the data. So in this case, we've got quantitative data, so we're going to be looking at x bar 1 and x bar 2. And in this case, we're going to be looking at the difference between those. So again, that value is not on the output screen, so you would actually need to compute the difference. X bar 1 and x bar 2 will be displayed there, and then we just need to perform the subtraction on those. The standardized test statistic formula, we've got this x bar 1 minus x bar 2 in the numerator, minus, again, and then in parentheses, mu1 minus mu2. But again, in this class, mu1 minus mu2 in null hypothesis is always going to be equal to 0. So this will just be 0 always for us. So we can just write the numerator as x bar 1 minus x bar 2. And then our denominator for the standard deviation formula here, we've got the square root of our variance from group 1 divided by n1 plus the variance from group 2 divided by n2. And again, we're going to get that final value just off the output screen when we run the test. The O is to obtain the p-value, so again, we're going to use technology to get that, whether it's a calculator or StatCrunch, and we're going to draw a picture of that distribution to make sense of the numbers. And then steps 7 and 8, making a decision and stating a conclusion, exact same logic as we've had before. All right, the confidence interval, we're going to follow through the steps for panic. Again, it's quantitative data, so again, our parameters are going to be mu1 and mu2. Random variables x bar 1 and x bar 2. Same assumptions we just talked about for the other test. And so if those conditions check out and we want a confidence interval, we're going to run a two-sample t-interval on the calculator. And that will give us our point estimate and interval estimate for this difference. So again, the sample statistics, quantitative data, they will be x bar 1 and x bar 2. And then in particular for two groups, we're going to be looking at that difference, x bar 1 minus x bar 2. And then the confidence interval is going to be, again, on that output screen for us. Okay. And using StatCrunch, again, the endpoints are called lower limit and upper limit. So again, no matter which technology we use, we're going to get these values for our point estimate and our interval estimate. And then our conclusion, again, depends on, again, we're looking at a difference. So we're looking at if we subtract, do we get positive things? Do we subtract and get negative things? Or if one endpoint is negative and one is positive, then we don't have any evidence of a difference in the groups. Okay, so if they're both positive, then we know that the mean measurement of all the objects in group 1 is more than the mean measurement of all the objects in group 2, finding an amount somewhere in that interval. But if both the endpoints are negative, then we're going to say that we're C% confident that the mean measurement of all objects in group 1 is less than the mean measurement of all objects in group 2 by an amount in that interval, where again we drop the negatives because that's taken care of with the less than. Where's less than? That's why, so again, these absolute values just mean to write those endpoints without the negative sign. So be careful not to have negative numbers in your interpretations here.